Welcome to our tutorial on inverting amplifiers. Today, we're going to explore how an inverting amplifier works using this circuit diagram you see on the screen. By the end of this video, you should have a solid understanding of the basic principles and workings of an inverting amplifier. First, let's identify all the components in our circuit. We have an operational amplifier, or op-amp, which is the heart of our amplifier circuit. Two resistors, one with a value of 1 k-ohm and another with a value of 3 k-ohm. An AC signal source that generates a 40 Hz sine wave. Now, let's talk about how these components are connected. The AC signal source is connected to the inverting input of the op-amp through the 1 k-ohm resistor. The non-inverting input of the op-amp is connected directly to the ground. The 3 k-ohm resistor is connected between the output of the op-amp and the inverting input. This configuration is known as an inverting amplifier because the input signal is applied to the inverting input of the op-amp, which will cause the output signal to be inverted, or phase shifted by 180 degrees, compared to the input. Now, let's dive into the working principle of this circuit. The op-amp has two inputs, the inverting input and the non-inverting input. The basic function of an op-amp is to amplify the difference in voltage between these two inputs. In our circuit, the non-inverting input is connected to the ground. This sets its voltage to 0 volts. Due to the high gain of the op-amp, the inverting input will also be held at a voltage very close to 0 volts. This point is called a virtual ground. When an AC signal is applied to the inverting input through the 1 k-ohm resistor, the op-amp works to keep the inverting input at the virtual ground. To do this, it adjusts the output voltage accordingly. This creates a situation where the input signal is inverted at the output. Let's talk about the feedback mechanism. The 3 k-ohm resistor is connected between the output and the inverting input. This resistor forms a feedback loop, which is crucial for the operation of the inverting amplifier. The feedback ensures that the op-amp stabilizes and accurately inverts and amplifies the input signal. To understand how much the input signal is amplified, we use the concept of gain. For an inverting amplifier, the gain is given by the formula. Gain equals negative RF over Rn, where RF is the feedback resistor, 3 k-ohms, and Rn is the input resistor, 1 k-ohm. Let's plug in our values to calculate the gain. Gain equals negative 3 k-ohms over 1 k-ohm equals negative 3. This means that our output signal will be 3 times the amplitude of the input signal but inverted in phase. Now, let's look at the signals. Our input signal is a 40 Hz sine wave with a peak voltage of 5 volts. Given our calculated gain of negative 3, the output signal will be a 40 Hz sine wave with a peak voltage of 15 volts but inverted. The waveform you see here confirms this. The output signal is an inverted version of the input signal with a higher amplitude. Let's go over a few practical applications of inverting amplifiers. Signal conditioning. Inverting amplifiers can be used to adjust the amplitude of signals for further processing. Audio amplification. They can amplify audio signals in sound systems. Analog computing. Inverting amplifiers are used in analog computers to perform mathematical operations. To sum up, an inverting amplifier takes an input signal, inverts it, and amplifies it by a factor determined by the ratio of the feedback resistor to the input resistor. In our example, the output is 3 times the input amplitude but inverted, thanks to the op-amp and the feedback resistor. I hope this tutorial has helped you understand the basics and workings of an inverting amplifier. If you have any questions or need further clarification, feel free to ask in the comments below. Thanks for watching.